Good morning, students. So, love to see you all in the morning, and we have studied some concepts related to invertible functions in the last video, and this is just continuous to that video only. And in this video, we are going to learn some important properties of invertible function, and this is your last concept of the chapter, right? So before coming to the properties of invertible function, I would like to recall the invertible function definition in composition language. So how we can define the invertible function, as definition itself speaks. If f is a function from x to y, then there exists a unique function g y to x, then such that g circle f of x is x and f circle g of y is y. If these two functions satisfying these two conditions, then g is called the inverse of f. It is written as f inverse is equal to g. So we have discussed these points through our questions yesterday, that is what in the last video. Now we are going to use this definition to prove three important properties of invertible functions. Okay, so first I will elaborate the definition little bit more before going to that 3 points. So what is that here? F is a function x to y, g is a function from y to x, then g circle f of x is x, f circle g of y is y, then we can say that g is the inverse of f. So I am writing this again by speaking like, I am just modifying the definition a little bit. I am writing here double implies. What is by double implies here? If inverse of the function is g, it also implies that g circle f of x is x, f circle g of y is y. So I can use the definition vice versa type. If any two functions, f is a function, g is a different function, if these two functions satisfying these two conditions, hence g is called the inverse of f. Similarly, if g is the inverse of f, we can say these two conditions are universally true. So here, if g is the inverse of f, it means that in these two conditions, I can replace g with f inverse. So therefore, I can speak the same conditions in terms of in f inverse, that f inverse circle f of x is x and f of f inverse of y is y. I repeat, I simply replace g with f inverse in these two conditions. So hence, if g circle f of x is x, then f inverse circle f of x is also x. Similarly, f circle g of y is y, then f circle f inverse of y is also y. So why I am writing these two statements is that this will be a very useful statements when we prove some important properties based on invertible functions. So now we are move on to the properties of invertible functions. So let's see the first property of the invertible function. What is the first property of invertible function? Is inverse of inverse is a function itself, but the condition is if f is invertible. I repeat, if f is invertible function, inverse of inverse is again the function itself. Now we are going to prove this statement theoretically. See how. Let there is a function f which is x to y is invertible. It means which is bijective function. So it implies that its inverse is defined from set y to x, as the definition speaks. It also implies that inverse of inverse, it means that inverse of this function is defined from again x to y. So here I can say f is a function defined from x to y, then inverse of inverse is also defined from same x to y. So they are coincide. Therefore f inverse of inverse is the function itself. So this is the derivation of this property. So I repeat, if f is a function invertible, then inverse of inverse is the function itself. So the theorem is there and the proof is here. So I think you will understand this theorem. So now we'll move on to the second property of the invertible function. Now see, what is the second property of the invertible function? See, if f is invertible, if f is invertible, there exists unique inverse. Unique inverse. It means that every invertible function has one and only one inverse. Every invertible function has one and only one inverse. So this is the important property of invertible function. Now we are going to prove this statement theoretically by using the contradiction method. I am going to use a contradiction method. For that, what I am assuming that there are two different inverses possible of given invertible function f. So I am assuming let g1 and g2 are the two inverses of the function f. So by the definition I can speak here, if g1 is inverse of f, then definitely g1 circle f of x must be equal to x, because already we have discussed this point. If g is the inverse of f, we can say that g circle f of x must be equal to x. So by this definition I can write g1 circle f of x is x, because I already assumed that g1 is the inverse of f. Similarly I can also speak, if g2 is the inverse of f, then g2 circle f of x is also x, because the reason is saying that g circle f of x is x if g is the inverse of f. Now from these two statements you can also speak here, if both the results are coincide with x, we can simply say g1 circle f of x is equal to g2 circle f of x. So we can simplify this statement further by eliminating these circles. It means that g1 of f of x is equal to g2 of f of x. And what is f of x here? Which is simply that it is y. g2, what is f of x? Again it is y. So there is no question, because if you assume the function which is from x to y, so definitely f of x will give what? Y only. So that's why I am replacing this f of x with y. And ultimately, if g1 and g2 are the inverses, so g1 of y will give x, g2 of y will also give x, because f is a function from x to y. If g1 is the inverse of the f, g1 would be defined from y to x, g2 also defined from y to x. In the same manner, g1 of y will give x, g2 of y will also give x. So hence we can say that though we are assuming g1 and g2 are the two different inverses function of the f, but here these two functions are coincides. So therefore we can say here G1 is equal to G2. Hence these two functions are same. So this theoretical proof speaks the same sentence that every invertible function has one and only one inverse. So this is your point number 2, or property number 2 from the invertible functions. So we'll move to the third property, that is the last property of the invertible function in our syllabus. So this third property is been asked in boards many a times. So please be careful and please learn these theorems very thoroughly. Okay. So now the third property speaks what? If f is a function from x to y and g is another function from y to z are invertible functions. These two functions are individually invertible, then their composition is also invertible. I repeat, f and g both are invertible function, then their composition is also invertible. And we know what is the composition of f and g? That is defined as g circle f, which is defined from set x to set z. Set x to set z is also invertible. I repeat, if f and g are two different functions which are already invertible, then their composition is also invertible. And here, if this is a function which is invertible, then its inverse g circle f, that is composition of two functions, inverse is defined as f inverse circle g inverse. So this is the inverse of the composition function. Now what we are going to prove is inverse of composition of two function is always like f's inverse circle g inverse. In a reverse order it opens, right? If g circle f of whole inverse is equal to f inverse circle g inverse. So to prove this, I am using the fundamental definition of invertible functions. As you know, f is a function which is defined from x to y and its inverse is exists, then it is defined from y to x, and it also implies that f's inverse f of x will always give x, and f circle f inverse of y will also give y. So if f is invertible function, they must satisfy these two conditions. So here, if g circle f is invertible function, so its inverse is given by this way. So we are going to prove this statement is always true by considering g circle f is a single function whose inverse is given by this. So here in place of f we have g circle f, in place of f inverse we have this operation. I repeat, f is a function x to y, so we can consider in place of f g circle f is a single function whose inverse is defined as this. So I am taking this function now to prove. See, how can we prove this statement? Simply, if I am able to prove these two conditions are true with this inverse, so I can say that this is the inverse of this function. Okay, for that I am taking this statement, f inverse circle f of x is equal to x. And what is the inverse here? See, let this is considered as a function, g circle f as a function whose inverse is this. So I am taking here, let g circle f is the function defined from set x to set z, because already it is being defined in the definition. Set x to set z. So it implies that f inverse, or we can also speak like g circle f whole inverse, that is inverse of this function, is defined from z to x. It also speaks that f inverse circle g inverse is also what? Z to x. So now if g circle f is from x to z, then f inverse circle g inverse from z to x. So these are the two functions which are inverse of each other. Now we are going to prove this operation is true in this case. Okay, right. So what is the function we are taking? G circle f is a function from x to z. Then what we have? F inverse circle G inverse is from z to x. If this is a function, this is the inverse. Composition is a function, then inverse is this. Now if these two are inverse of each other, they must satisfy these two conditions. So I am taking the first condition only. So what is the first condition speak? Inverse of the function circle function of x is equal to always x. So what is the inverse of the function? This is inverse and this is a function. So this circle this of x must be x. So that is what I am going to write. So f inverse circle g inverse, inverse of the function circle function. So inverse of the function f of x must be equal to x. This is what we are going to prove. So now I am taking the left hand side portion to prove this. So I can write here f inverse circle g inverse, right, of g of f of x. As you know, how can we eliminate these circles? Now what is f of x? F is a function from x to y. Then what is f of x? Will give y. So I am writing this f of x with y. So f inverse g of y. So now what is g of y? Because g is a function from y to z. So g of y will give z. So I am replacing this g of y with z. So it implies that f inverse circle g inverse of z. Now I am repeating here. It can also written as f inverse g of z. G inverse of z. So what is g inverse of z? I repeat, what is g inverse of z? Now first coming to this function. Here g is a function from y to z is already invertible. It means that its inverse is defined from z to x, z to y. So I can say that g inverse z will give what? Y. I repeat, f inverse. G inverse of z is given as y. And what is f inverse y will give? X, because f is a function from x to y. Its inverse is defined from y to x. Hence f inverse y will give x. So ultimately its answer is x. So now from this theorem we can say that if satisfying this condition, so similarly it also satisfies the second condition. I can simply say now inverse of the composition function g circle f of inverse is equal to f inverse circle g inverse. So this property going to be a universal. Means that I mean to say that you may write in a generalized form of this statement here. Let us say there are three functions which are invertible. F, G and H are invertible. So their composition is also invertible. It means that ki F circle, G circle, H whole inverse written as how can we write this? So when you are writing the inverse of the composition of function, it always open in a reverse order. It means G circle f of inverse is equal to what? F inverse circle G inverse. So in the same manner you can open this. Fine. So now we are going to discuss one important question which is being asked in a boards. So let's discuss that question, and that is the last point to be discussed, and then we will end up with the video. Fine. So I am taking one question which has been asked in boards. Now see. The question is, f is a function which is defined from R to R, and f of x is equal to 2x minus 3, and g is also a function from R to R, and g of x is defined as x cube plus 5. So what they are asking that key find fog and golf, find FOG, fog and golf, and also prove that fog is invertible. Fog is invertible. Also find that key inverse of the fog. What is the inverse of this composition of the function? And then find fog inverse of the value 9. So there are 4 questions in a chain. What is that they are asking? If f is a function from real numbers to real numbers and the function is given as 2x minus 3, g is a function R to R, real numbers to real numbers, defined as x cube plus 5, then find 4 things in a chain. First we'll find fog, that is composition of 2 functions, and then we'll prove fog is invertible, and then we'll find its inverse also, and then we'll find this one. So there are 4 questions in a chain. It's a long type question being asked for 4 marks, right? So now we're going to find fog, thereafter we'll prove invertible, then we'll find inverse, then with the help of inverse we'll find inverse of 9. Okay, so now first we'll take the first part. What is the first part of this question? We are going to find fog. And what is a fog means? F of g of x. So in short we can write it as f of g of x, because fog can also written as fog of x, which implies that f of g of x. And what is g of x? We have x cube plus 5, right? And then what is f of x cube plus 5? In place of x we are going to substitute this function, so we can write it as 2 times of x cube plus 5 minus 3. So hence the function which you obtained as 2x cube plus 10 minus 3, which reduced to 2x cube plus 7. So this is the fog function we got. So therefore the fog of the function is given as 2x cube plus 7. The first part is done. Now if fog is done, what we are going to prove? Fog is invertible, means we are going to prove this function is invertible function. This function is invertible function where fog is defined from R to R only. So I am taking this result to prove the second one, because these all 4 parts are in a chain interdependable, one after the other. Fine. I am just writing the final result here. What we are got 2x cube plus 7. Right. So fog, which is defined from real numbers to real numbers, and what we obtained here, fog is a function which was 2x cube plus 7, correct? So this was the result. Now we are going to prove this function is invertible, and again we have two options to prove invertible. Either we go with bijective function or we go with composition of the function. So I am here going with one one and onto, that is bijective method. First I will prove it is one one and then onto, then I can simply declare that this function is invertible. Okay, so to make it simple, to make it convenient to speak, so I am assuming for time being the fog with some other function, let's say some h. So I am just assuming that this fog is a composition of this function is h function. So I can write the same statement with h is a function defined from R to R, where h of x is given as what, 2x cube plus 7. So instead of proving this, I am proving this is 1 1 and onto. So first, for 1 1 function, what I can write, let h of x1 is equal to h of x2, where x1 and x2 belongs to real numbers. Hence, what is h of x1? 2x1 cube plus 7 is equal to 2x2 cube plus 7. So I can simply cancel 7 and 7. So next step will be 2x1 cube is equal to 2x2 cube, then 2 to get cancelled. Hence x1 cube is equal to x2 cube by taking cube root on both the side. Otherwise, and I can also speak that simply x1 is equal to x2, because cube root of positive number is positive, cube root of negative number is negative, and x1 and x2 belongs to R. I can simply say that x1 is equal to x2. If you are not understanding this last statement, I can also speak in other way. See, by shifting this term to the left hand side, x1 cube minus x2 cube, which is equal to 0. It means that a cube minus b cube is 0. I can simply say by using the factorized formula, a minus b into a square plus ab plus b square equal to 0. Since here x1 and x2 belongs to the real numbers, I could say that this cannot be equal to 0, because it always gives some positive numbers, and there hence we can say that this cannot be equal to 0. Hence we can say x1 minus x2 must be 0, then x1 is equal to x2. So if h of x1 is equal to h of x2, it implies x1 is equal to x2. This satisfying the definition. Hence we can say that the h of x is 1 1. Now we are going to prove the same function is onto. Now, as you know how to prove onto, right? So I am taking this onto function. So how to prove onto function? For this, see. So let h of x, the given function, is equal to y. So what you will speak here? 2x cube plus 7 equal to y, and then we'll solve for x. So simply 2x cube is equal to y minus 7. Then it implies that x cube is equal to y minus 7 upon 2. So finally the x would be equal to plus minus cube root of y minus 7 upon 2. So this is the x we got. So here you can speak that for every value of y, you will able to get x. So hence we can say that this is onto function. So I can speak again here, for every value of y which is belongs to real numbers, we can able to get x, which is belongs to what? real numbers. Hence, we can say that h of x is onto. So here we are able to prove the given function is 1, 1 and onto. Hence it is bijective function. If it is bijective function, you can simply say the fog is invertible function. And what is the inverse of this function? Simply from this operation you can say the term in terms of y, the operation which you got is called inverse of the function. So h of x is 2x cube plus 7, then h inverse x is given by cube root of y minus 7 by 2. So ultimately the third part answer would be what? Third part का answer क्या होगा? The inverse of this fog function is given by cube root of y minus 7 upon 2. So in short, we are able to prove fog is invertible and its inverse is given by cube root of y minus 7 by 2. Now with the help of this inverse function, now we are going to find fog inverse 9 value. That's the last part. Now what is the last part? So what we got, the inverse of this function, fog inverse is equal to cube root of y minus 7 upon 2. So here you can write plus minus. Now what we are going to find, fog inverse 9. So fog inverse 9, it simply means that in place of y we are going to substitute 9 to get this value. So it is given by plus minus cube root of 9 minus 7 upon 2. So plus minus cube root of, it is simply 2 by 2. It is simply cube root of 1. And you know that cube root of 1 has 1 only. So hence we can say that ki f circle G inverse of 9 has the two values, plus 1 as well as minus 1. There are two possible values of this function. It means that 9 has the two pre-images under this function. So this is all about the question. So question was, if there are two functions defined like this and we have already found out the fog function and we have proven this as invertible, and then we got the inverse of the function. With the help of inverse of the function, we are able to prove inverse of 9 value is plus or minus 1. So this is a full length question. You can simply say that if two functions are invertible, then their fog is also invertible. That is what composition of two function is also invertible. So friends, here we are end up with the chapter even. We have already studied in the last video we have studied that the invertible function testing can be done in two different ways. The first one was bijective method, second one was composition method, and the subsequent video in today's video we have learned the three major properties of invertible function. That is, the first point was, if f is invertible, then we can say that f inverse of inverse is the function itself, inverse of the inverse function itself. The second point was, every invertible function possesses one and only one inverse. Every invertible function possesses one and only one inverse. The third point was, if f and g both individually invertible functions, then their composition is also invertible. I repeat, f and g both are individual functions, then their composition is also invertible functions. Hence, what we were saying that ki f circle G inverse is nothing but simply G inverse circle F inverse. It means that if you are finding the inverse of the composition, first G inverse will performed, then F inverse will performed. So this is the third point which we were discussed. So apart from the three important properties of invertible function, now we have discussed the one important question where we are finding these four parts. So I hope you have understood the topic very well. So though if you have not understood, if you have any doubts in this, so you can contact me on WhatsApp, or you may also share your doubts through mail. Okay, thank you and take care yourself.